You look at the night sky and think nothing changes. But on July 1st, 2025, a telescope in Chile caught something wrong. An object moving at 221,000 kilometers per hour, not bound to our sun, coming from outside. The third interstellar visitor we have ever seen, and this one spins so fast it should not exist. 3, I Atlas, that is the name astronomers gave it, rotates every 16.79 hours. That number sits on the knife edge between survival and destruction. One researcher from the Gran Telescopio Canarias on the island of La Palma measured that spin between July 2nd and July 5th using a 10.4 meter mirror. Raul de la Fuente Marcos led the team. They watched the comet brighten and dim with each turn. 16.79 hours plus or minus 0.23 hours. Another team led by Tony Santana Raz tracked it from July 2nd through July 29th using multiple telescopes. They got 16.16 hours plus or minus 0.01 hours. Close numbers. Same message. This thing is spinning near its limit. Most comets rotate slowly. Comet 67, P. Churyumov-Gerasimenko, the one Rosetta landed on, turns once every 12.4 hours. That nucleus measures 4.3 kilometers long. Comet Hale-Bopp spun around once every 11.35 hours with a nucleus reaching 40 kilometers across. Even Comet 41P Tuttle-Giacobini-Crasac, which astronomers watched slow down from 24 hours to 48 hours in just 6 weeks during 2017, never approached the danger zone that 3 I Atlas occupies. Here is what 16.8 hours means for a rotating body in space. At that speed, material at the equator experiences significant centrifugal force pulling outward. For a comet nucleus, 5 kilometers wide, the size 3 I Atlas might be, every chunk of ice and rock at the rim wants to fly away. Only 2 things stop it: gravity pulling inward, structural strength holding the pieces together. If the spin gets faster, the comet tears itself apart. If it slows down, it survives. 3, I Atlas sits exactly where those forces balance. The Atlas survey station at Rio Hurtado discovered it at a distance of 4.5 astronomical units from the Sun. That is 670 million kilometers out, beyond Mars, approaching from the general direction of Sagittarius. The survey took the first image at 05:15:11 Coordinated Universal Time. Within hours, astronomers knew this was not normal. The object traveled on a hyperbolic trajectory with an eccentricity above 1.0. That meant it would never return. Its hyperbolic excess velocity, the speed it carries even accounting for the Sun's gravity, measured 58 kilometers per second. For comparison, Voyager 1, our fastest human-made object leaving the solar system, moves at 17 kilometers per second relative to the Sun. 3, I Atlas goes 3 times faster. By July 2nd, multiple telescopes confirmed a diffuse coma. David Jewett and Jane Liu at the Nordic Optical Telescope on La Palma saw it clearly active without gassing. Miguel Alarcón and his team at the Instituto de Astrofísica de Canarias used the 2-meter twin telescope at Teide Observatory. Same result. A cloud of gas and dust extended 26,400 kilometers by 24,700 kilometers around the nucleus, twice Earth's diameter. The Minor Planet Center received 122 observations from 31 observatories before issuing the interstellar designation, 3Y, on July 2nd. The comet got the additional name C 2025 N1 Atlas. Pre-cover images pushed the detection timeline back. The Zwicky Transient Facility had captured it on June 28th and 29th without recognizing it. Then June 14th through 21st, then May 22nd, an amateur named Sam Dean found Atlas survey frames going back to June 5th. Nobody spotted it earlier because it crossed in front of the galactic center's dense star fields. Too many stars, too much background. The comet hid in plain sight. If you value documented astrophysics and interstellar object analysis like this, subscribe. It is the best way to support our work. Also, comment from which city you are hearing this from. Also, this script is researched and factual, using sources from the Wikipedia 3 I Atlas article, updated as of October 3rd, 2025. NASA's official 3 I Atlas page maintained by the Jet Propulsion Laboratory, and the paper by Raul de la Fuente Marcos and colleagues published using Gran Telescopio Canarias observations from July 2 through 5/20/25 SPAS. All cross-referenced with very large telescope spectroscopic data from the European Southern Observatory released August 21st, 2025. Now back to the information. The rotation rate became the first clue that 3I Atlas defies normal expectations. Comets are not solid rocks. They are rubble piles, loose aggregations of ice and dust held together more by gravity than by strength. Laboratory measurements on comet analog materials show tensile strengths between 1 pascal and 10 kilopascals. 1 pascal equals the pressure of a sheet of paper resting on a table. 10 kilopascals equals the grip strength of a human hand. That is fragile. Philae, the lander that touched down on 67P, measured a compressive strength of about 10 kilopascals at the Agilkia landing site. The CAS instrument recorded forces during touchdown on November 12, 2014. When Philae bounced, it scratched the surface and left marks. Analysis showed the comet material crumbled like packed snow. Comet nuclei have bulk densities between 400 and 600 kilograms per cubic meter. Water has a density of 1,000. Ice is 917. Solid rock ranges from 2,500 to 3,000. Comets fall far below. Comet 67P measured 532 kilograms per cubic meter from Rosetta navigation data. Comet 9P Tempel 1 came in at 620 with a margin of error reaching up to 1,090. Comet 81P Wild 2 returned a value around 500. The interstellar comet 2 Ibrisov, discovered in August 2019, likely matched 500 as well based on its behavior. That low density means comets are porous, 60% empty space or more. They resemble snowdrifts more than boulders. Microscopically, they consist of micron-sized grains of silicate dust and ice aggregated over billions of years. Macroscopically, they are collections of larger chunks weakly bound together. For a body that porous and that weak, rotation sets the survival limit. The critical breakup period depends on density and tensile strength. A simple relationship governs it. The minimum stable period in hours equals approximately the square root of 3 divided by the square root of the product of gravitational constant, density broken in a shape factor, with tensile strength added as a correction term. For a sphere of 500 kilograms per cubic meter density with 1 kilopascal tensile strength, the critical period sits near 16 hours for a body several kilometers across. Smaller than that, tensile strength dominates and the object can spin faster. Larger than that, self-gravity dominates and slower spins are required. 3I Atlas at 16.79 hours places itself right at that transition. Compare that to observed limits. Pravec and Harris analyzed asteroid rotation data in the year 2000. They found no asteroid larger than 40 kilometers rotates faster than 2.2 hours. Those large bodies are gravity-dominated rubble piles with negligible strength. Smaller asteroids, those under about 300 meters, can rotate much faster because material strength becomes significant at small scales. Comet C2011J2. Linear broke apart at a distance beyond 4 astronomical units from the Sun in 2011. Photometric analysis by multiple observers estimated its rotation period at 4.56 hours. Structural analysis suggested a cohesive strength greater than 0.9 kilopascals, assuming a bulk density of 500 kilograms per cubic meter. The comet fragmented anyway. Progressive splitting occurred over weeks as the nucleus lost pieces. Researchers concluded rotational disruption combined with sublimation pressure caused the breakup. Comet 41P Tuttle-Jacobini. Krisak provided a dramatic example. David Schleicher and colleagues at Lowell Observatory tracked it during its close approach in 2017. On March 19th, the rotation period measured 24 hours. 10 days later, it reached 27 hours. By early May, the period stretched to 48 hours, double the initial value in 6 weeks. The team observed jets of gas rotating clockwise, shutting off as their source regions moved into night and brightening as sunlight hit them again. If the comet continued slowing, it might stop completely in reverse direction. That spin down came from asymmetric outgassing creating torque on the nucleus. Gas jets acted like tiny rocket engines, changing the comet's angular momentum. The fact that it slowed rather than sped up meant the jets fired at angles that braked rotation. Matthew Knight, a collaborator on that study, noted that measuring rotation changes sets limits on density and internal strength when combined with nucleus dimensions. 3. IATLAS at 16.8 hours is not slowing down observably. At least, not yet. The comet remains stable at a period most similar-sized bodies could not sustain. That stability demands explanation. The first possibility. 3. IATLAS has higher tensile strength than typical comets. Maybe its material is more compacted, more sintered. Grains fused together by billions of years drifting through interstellar space. Collisions between interstellar grains can create material bridges. Sintering occurs when surfaces touch long enough for molecules to migrate and bond. Temperature cycling, heating and cooling over cosmic timescales, can harden icy material. If 3I Atlas spent 10 billion years in interstellar space, as some age estimates suggest, that gives time for strengthening. The comet could be an ancient relic from the thick disk of the Milky Way, ejected when its parent star system formed and spent eons hardening its structure. The second possibility. 3. I-Atlas is smaller than estimates suggest. A smaller nucleus has less gravitational binding and more contribution from material strength. If the actual diameter is 1 kilometer instead of 5, the critical spin period decreases, but observations constrain the size. Hubble space. Telescope images from July 21st and August 20th, 2025 show a nucleus between 0.44 kilometers and 5.6 kilometers in diameter. The uncertainty comes from separating the nucleus from the bright coma around it. The coma scatters light, making the nucleus appear larger. Infrared observations by the James Webb Space Telescope on August 6th detected carbon dioxide outgassing at 150 kilograms per second with an outflow velocity of 440 meters per second. That mass loss rate, combined with trajectory tracking over 4 months by 227 observatories worldwide, set a lower mass limit. The analysis by Richard Cloete, Peter Veers, and Avi Loeb published September 24th, 2025, found the nucleus mass exceeds 33 billion tons. At a density of 500 kilograms per cubic meter, that implies a minimum diameter of 5 kilometers. 3. I-Atlas is not small. The third possibility. 3. I-Atlas is not a normal comet. Its structure might differ fundamentally from solar system comets. It formed somewhere else under different conditions. Trajectory analysis by Matthew Hopkins and collaborators in July 2025 estimated an age between 7.6 and 14 billion years with 68% confidence. An independent study by Astor Taylor and Daryl Seligman reached 3 to 11 billion years. Both agree this object is ancient, older than the Sun, older than Earth, possibly older than the solar system itself. That age comes from the comet's velocity and the part of the galaxy it likely originated from, the thick disk which contains older stars. A comet that old experienced a different formation environment. The early Milky Way had different chemistry, different dust compositions, different ice mixtures. If 3I Atlas formed before the solar system, its internal structure might reflect primordial conditions we do not see in local comets. Spectroscopic observations add more strangeness. The Very Large Telescope in Chile observed 3I Atlas on July 20th and detected atomic nickel vapor in the coma. That is not unusual. Many comets emit nickel, but no iron vapor appeared. Normally, nickel and iron outgas together in roughly equal amounts. Here, nickel showed up alone. By August 14th, the VLT also detected cyanide emission. Throughout July and August, nickel and cyanide concentrations increased steadily as the comet approached the Sun and activity ramped up. On August 21st, the comet released 4.6 grams of nickel per second and 17.6 grams of cyanide per second. That nickel to iron ratio, nickel present, iron absent, does not match solar system comets well. The James Webb Space Telescope examined 3I Atlas on August 6th with its near-infrared spectrograph. The spectra showed unusual richness in carbon dioxide. Most comets are water-rich. 3I Atlas is carbon dioxide, rich with only a small amount of water ice, water vapor, carbon monoxide, and carbonyl sulfide. The coma composition suggests a nucleus dominated by frozen carbon dioxide rather than water ice. That composition is rare. It indicates formation in a colder region or under conditions favoring carbon dioxide retention over water. Either the comet formed farther from its parent star than typical Kuiper Belt objects, or it formed in a molecular cloud with unusual chemistry, or it lost water preferentially during its long interstellar journey. NASA's SPHEREx mission observed 3I Atlas from August 7th through August 15th. Infrared imaging revealed an extensive carbon dioxide gas coma spanning at least 348,000 kilometers in radius, more than 13 times the visible coma size. This invisible infrared halo extended far beyond what optical telescopes could see. The carbon dioxide sublimated from the nucleus surface, creating a vast bubble of gas molecules moving outward at hundreds of meters per second. That immense coma carried mass away from the nucleus continuously. Yet the nucleus did not change its rotation rate observably. Here is the paradox. A rotating comet sheds mass asymmetrically. Sunlight heats the day side. Ice sublimates. Gas erupts from active regions. Those gas jets carry momentum. When a jet points in a certain direction, it pushes the nucleus the opposite way by conservation of momentum. If jets are not symmetric, they create torque. Torque A changes rotation. Comet 67. P sped up and slowed down over months as jets fired from different regions during its orbit. Rosetta's flight dynamics team measured rotation period changes of several minutes over months. Comet 40. 1P slowed dramatically from jets, breaking its spin. 3. I-Atlas releases 150 kilograms per second of material moving at 440 meters per second. That is a momentum flux of 66,000 newton-seconds per second, or 66,000 newtons of thrust. Continuous thrust of that magnitude acting on a 5-kilometer nucleus should change the rotation period by a measurable amount within weeks. The astrometric data spanning May 15th to September 23rd, 4.5 months, show no deviation from a purely gravitational trajectory. The comet travels where gravity says it should go with an upper limit on non-gravitational acceleration of 15 meters per day squared. That absence of observable acceleration is the clue. If 3 I-Atlas releases 150 kilograms per second symmetrically, the thrusts cancel and no net torque results. But comets are not symmetric. Nuclei have irregular shapes. Active regions cluster in patches. Some areas face the sun while others remain in shadow. 67P showed discrete jets from specific locations on the nucleus. Comet 1P Halley exhibited jets from active areas that shut off when those regions rotated into night. Asymmetric outgassing is normal. Yet 3 I-Atlas, despite releasing gas at 150 kilograms per second, shows no sign of the asymmetric acceleration such jets should cause. Either the outgassing is perfectly symmetric by improbable chance, or the nucleus is massive enough that the jets barely affect it. 33 billion tons. That is the lower limit on mass from the lack of non-gravitational acceleration. For comparison, the interstellar object, 1I Oumuamua, discovered October 2017, had an estimated mass around 400,000 tons with a length of 230 meters. Interstellar Comet 2, I Borisov, discovered August 2019, measured about 0.5 kilometers across and massed tens of millions of tons. 3. I-Atlas at 33 billion tons is 3 to 5 orders of magnitude more massive, 1,000 to 100,000 times heavier. It constitutes a major anomaly in the distribution of interstellar objects. Avi Loeb, in his analysis with Cloete and Veers, noted that given the limited reservoir of heavy elements ejected from exoplanetary systems, astronomers should have discovered around 100,000 interstellar objects on the 0.1 kilometer scale of Oumuamua before finding one as large as 3 Dwarf Atlas. Yet only 2 prior interstellar objects were detected. The size distribution appears inverted. That anomaly raises the question of what 3 I-Atlas actually is. A comet of normal composition would have the expected density and strength. A 5-kilometer nucleus at 500 kilograms per cubic meter, spinning at 16.8 hours balances exactly on the edge. But if the composition is unusual, more carbon dioxide, less water, different silicate content, the density could differ. Carbon dioxide ice has a density of 1,560 kilograms per cubic meter at low temperature. Water ice sits at 917. If 3. I-Atlas contains more carbon dioxide ice and less empty space, the bulk density increases. 600 kilograms per cubic meter instead of 500, 700, maybe 800. Higher density increases gravitational binding. That allows faster stable rotation for the same size, but there is a ceiling. At a certain density, you stop calling it a comet and start calling it something else. Rock has a density of 2,500 to 3,000. Metal goes higher. If 3 I-Atlas were solid metal, its density could reach 8,000, but spectroscopy shows ices sublimating. Carbon dioxide, water. Cyanide. Those are volatile ices that require comet-like material. Metal does not sublimate at distances of 2 to 4 astronomical units from the sun. The object is releasing material. It has a coma. It is a comet, just a strange one. The rotation period, 16.79 hours, does not change observably over months, despite massive outgassing. That means either the torques perfectly cancel, or the moment of inertia is large enough that torques do not matter on observable timescales. Moment of inertia depends on mass and how that mass is distributed. A solid sphere has a different moment of inertia than a hollow shell or an elongated rod. If 3 I-Atlas is elongated, shaped like Oumuamua, but much larger, the rotation period measurement might correspond to tumbling rather than simple spinning. Tumbling objects have complex rotations. They spin around multiple axes. Observing tumbling from a distance can give misleading period measurements because brightness variations come from both shape and orientation changes. But 2 independent teams measured similar periods, 16.79 hours and 16.16 hours. Close agreement. If the object were tumbling chaotically, different observing campaigns would measure different apparent periods depending on viewing geometry. The consistency suggests simple rotation around a single axis. That simplicity adds to the mystery. A comet that old, that traveled that far, probably collided with something during its journey. Collisions can set tumbling motion, yet 3I Atlas spins cleanly. Some researchers propose the comet might be a fragment. Hubble infrared observations by an unnamed team in August 2025, published in a paper accessible through the NASA Space News site on August 10th, suggest 3I Atlas may have been part of a larger body before a catastrophic event. Possibilities include collision with another object or tidal disruption near a massive planet. The current nucleus could be a surviving fragment of an original parent body. Trajectory analysis traced the comet's path backward through interstellar space. It likely came from a young star system where gravitational interactions ejected it. An ejection event might involve passing near a giant planet. Tidal forces from a close flyby could pull a comet apart. The pieces separate, some escape, others fall back together loosely. The result is a rubble pile with a particular mass distribution determined by how the original body broke apart. Comet Shoemaker-Levy. 9 provides an example. Jupiter captured that comet into orbit. On its last perigove passage in July 1992, the comet passed 1.3 Jupiter radii from the planet center, 93,000 kilometers. Tidal forces exceeded the nucleus structural strength. The comet shattered into at least 21 fragments. Those fragments spread into a string of co-moving objects. Each fragment was a small nucleus surrounded by its own coma. Numerical simulations of the breakup by Asphog and Benz in the mid-90s tested different density values. The best fit came from a bulk density of 500 to 600 kilograms per cubic meter. The original nucleus before disruption had a diameter of 1.6 kilometers. After breaking apart, the fragments ranged from 100 meters to a few kilometers. If 3I Atlas experienced similar disruption billions of years ago, the surviving fragment we see now might be the largest piece. It retained enough mass to remain gravitationally bound and coalesced into a stable object, but the structural memory of that disruption remains. Internal fractures, boundaries between coalesced chunks. Variation in density and strength from place to place. That heterogeneity could affect rotation stability. A fragmented interior might absorb torques differently than a monolithic body. When outgassing creates forces, those forces propagate through a fractured structure in complex ways. Stress concentrates at weak points. Material shifts. The net result could be a damping effect where the nucleus absorbs angular momentum changes internally rather than expressing them as observable rotation rate changes. The density discussion returns to the Roche-Limit. That is the distance at which tidal forces from a massive body overcome a smaller body's self-gravity and tear it apart. The limit depends on the densities of both objects and the strength of the smaller object. For a fluid body with no structural strength, the rigid body Roche-Limit is approximately 2.46 times the radius of the larger body, times the cube root of the larger body density divided by the smaller body density. For Earth and a moon made of rock, the limit sits at around 18,000 kilometers. For Jupiter and an icy comet, it lies near 128,000 kilometers. Comet Shoemaker-Levy. 9 passed at 93,000 kilometers and broke apart, suggesting its structural strength was negligible. But 3I Atlas is not near a planet. It is not experiencing tidal disruption from an external body. The Roche-Limit concept applies internally. Within the nucleus itself, every part pulls gravitationally on every other part. At the surface, the outward centrifugal force from rotation opposes the inward gravitational attraction. The boundary between staying together and flying apart depends on rotation rate. Spin too fast, and you create your own internal Roche-Limit situation where the equator wants to separate. That is the rotational breakup condition. The calculation is straightforward for a sphere. Centrifugal acceleration at the equator equals the radius times the angular velocity squared. Gravitational acceleration at the surface equals the gravitational constant times the mass divided by the radius squared. Set centrifugal equal to gravitational and solve for angular velocity. You get the breakup angular velocity. Convert to period. The result scales with the square root of density. If density doubles, the minimum period increases by the square root of 2, or about 40%. If density halves, the minimum period decreases by the same factor. For a 500 kilogram per cubic meter comet 5 kilometers across, the gravitational acceleration at the equator is about 0.0017 meters per second squared. The centrifugal acceleration at 16.8 hour rotation period is about 0.0012 meters per second squared. They are close, not quite equal, because tensile strength adds a small contribution holding the surface material in place. If the rotation period dropped to 14 hours, centrifugal would exceed gravitational even with tensile strength. The equator would shed material. If the period increased to 20 hours, gravitational binding dominates more clearly. 16.8 hours is the knife edge. 3 I Atlas occupies that edge and does not fall off. For months, no observable spin up or spin down. The comet remains locked at the critical period. That lock suggests a regulatory mechanism. That lock suggests a regulatory mechanism. A natural governor preventing the comet from tearing itself apart. The universe does not often create systems balanced on a razor's edge without a process to keep them there. For 3, I Atlas. This process must be powerful enough to counteract the continuous thrust from 150 kilograms of gas erupting every second. The question is not just how the comet survives, but what physical law enforces its survival. One proposed mechanism is a form of negative feedback. Imagine the comet as a spinning lawn sprinkler. The jets of water push back on the arms, making it rotate. For a comet, jets of gas do the same. If these jets are angled slightly against the direction of rotation, they create a braking torque, slowing the comet down. As seen with 41P Tuttle-Giacobini-Crasac, if they are angled with the direction of rotation, they create an accelerating torque, spinning it up. The mystery of 3, I Atlas, is that the net effect is 0, not approximately 0. 0 within our ability to measure over months. The self-regulation hypothesis proposes that the rotation rate itself controls the outgassing in a way that prevents runaway acceleration. Picture the equator of this 5-kilometer rubble pile spinning every 16.8 hours. The material there is barely hanging on. It is a zone of profound weakness. If the comet's rotation were to speed up, even slightly, to 16.7 hours Ballard, for instance, the centrifugal force would finally overcome the feeble combination of gravity and tensile strength. The loosest material, the dust and ice and pebbles at the very rim, would lift off. It would not erupt in a violent jet, but would instead be gently shed into space. This shed material carries angular momentum. Because it is liberated from the equator of a spinning object, it flies off tangentially. Moving in the same direction the surface was rotating. According to the law of conservation of angular momentum, if you eject mass in the direction of spin, the main body that is left behind must slow down. It is the same principle a figure skater uses. When they extend their arms, increasing their rotational radius, their spin slows. By shedding mass from its equator, 3 I Atlas would effectively be extending its arms, transferring angular momentum to the lost material, and slowing its own rotation in response. This creates a perfect feedback loop. If some random alignment of jets causes the comet to spin faster, it approaches its breakup limit. As it crosses that threshold, it begins to shed mass from its equator. This mass loss acts as a brake, slowing the rotation back down to the stable 16.8-hour period. The comet cannot spin itself to death because the very act of beginning to do so immediately stops it. It is a system that is dynamically stable at its point of instability. The comet is perpetually on the verge of destruction, held in check by its own rotational shedding. This model explains the stability, but it implies something profound. It suggests that 3 I Atlas is constantly losing a belt of material from its equator, a river of dust and gas flowing away, not in focused jets, but as a diffuse sheet peeling off the rim. This would be a form of outgassing fundamentally different from the sun-driven sublimation jets we see on other comets. It would be mechanically induced, driven by rotation. Astronomers are now searching for evidence of this equatorial shedding. It would be difficult to see. The material would be diffuse, spreading out in the plane of the comet's rotation, and might be lost in the glare of the much brighter coma produced by solar heating. But if detected, it would be strong evidence for a body governing its own spin. However, this only explains why the comet does not speed up. It does not explain why it does not slow down. The massive outgassing driven by sunlight should still be applying torques. Why do those torques not break the rotation, sending the period to 17 hours or 18 or 20? For the self-regulation model to be complete, there must be a corresponding mechanism to counteract any slowing. This is harder to explain. Perhaps as the comet slows, the equatorial shedding stops. The internal pressure from sublimating ices, no longer able to escape from the equator, builds up. This pressure could force open new vents or activate dormant jets in just the right orientation to apply a spin-up torque, pushing the comet back toward its critical limit. It would mean the comet is in a constant, delicate dance, shedding mass to slow down and firing jets to speed up, all to maintain its 16.8-hour equilibrium. A second possibility is more radical. It suggests our basic assumption that 3I Atlas is a single, coherent object is wrong. The consistency of the rotation period is one of the strongest arguments for it being a simple rotator. But there is a way to have a consistent period without a single body, a binary system. What if 3I Atlas is not one nucleus, but two smaller bodies orbiting each other, either in very close proximity or actually touching? This is known as a contact binary. We have seen such objects in our own solar system. The New Horizons spacecraft flew past 486958 Arrokoth, a Kuiper Belt object, on January 1st, 2019. The images it sent back were astonishing. Arrokoth was not a single sphere or potato shape, but two distinct, flattened lobes fused together at a narrow neck, looking like a reddish snowman. The two lobes, nicknamed Ultima and Bathul, orbit their common center of mass with a period of about 15.92 hours. That number is remarkably close to the period of 3I Atlas. If 3I Atlas is a contact binary, the 16.79-hour period we measure is not the spin of a single object on its axis. It is the orbital period of the two lobes revolving around each other. This structure is inherently more stable against rotational disruption. The gravitational bond between the two lobes provides a powerful anchoring force. The entire system has a much higher moment of inertia than a single body of the same mass, making it far more resistant to being spun up or slowed down by outgassing torques. This model also elegantly explains the lack of observable non-gravitational forces. Outgassing from a contact binary could be channeled in unique ways. The neck region between the two lobes would be a complex area of shadow and reflected sunlight. Ices there might sublimate differently. It is plausible that gas jets are directed primarily outward along the axis of rotation, perpendicular to the orbital plane. Such polar jets would produce no torque and would not alter the spin. Alternatively, outgassing from one lobe might be mirrored by similar outgassing from the other, causing their respective torques to cancel each other out. A system of two bodies provides more ways to achieve the symmetry required to explain the comet's perfectly gravitational trajectory. The formation of such an object fits well with its proposed history as a fragment. If a much larger parent body was shattered by a collision or tidal disruption billions of years ago, the resulting cloud of debris would contain countless fragments. In the aftermath, some of these fragments would have gently reaccumulated. A slow, gentle collision between two of the larger pieces could result in them sticking together, not as a rubble pile, but as a contact binary, their mutual gravity holding them in a delicate embrace. They would have been orbiting each other like this for billions of years. A silent dance through the interstellar dark. Detecting such a structure from our distance is exceptionally difficult. We cannot resolve the nucleus into two separate lobes. The entire object is just a point of light hidden inside a vast coma, but astronomers can look for secondary clues. As a two-lobed object rotates, the shape it presents to us changes. The light curve, the plot of its brightness over time, might show a more complex pattern than that of a simple ellipsoid. It might have two distinct peaks and troughs of different depths per rotation. Both teams that measured the period noted the light curve was regular, but more detailed analysis is underway to search for the subtle signature of a contact binary. This brings us to the deepest question of all, the origin. The composition of 3I Atlas is not just strange, it is a fingerprint, a message about where it came from. The high abundance of carbon dioxide ice over water ice, the presence of atomic nickel vapor without iron, these are not features of comets from our own Oort cloud or Kuiper Belt. They point to a formation environment that was chemically and physically different from the one that birthed our solar system. A standard comet is a primordial object. It is an agglomeration of the very first solids to condense from the protoplanetary disk. It is a loose collection of dust and ice that was never part of a larger, organized body. Its composition reflects the raw ingredients of its solar system. But what if 3I Atlas is not primordial? What if it is the product of destruction? Consider a large, distant world in another star system, a dwarf planet, similar in scale to Pluto or Eris, a body large enough, perhaps 1,000 kilometers in diameter or more, to have undergone planetary differentiation over millions of years. Heavier elements like iron and nickel would sink to form a small, rocky or metallic core. Lighter silicate materials would form a mantle around it, and the outermost layers would be a thick crust of various ices, water, nitrogen, methane, and, crucially, carbon dioxide. This body would not be a uniform rubble pile. It would be a layered world. Now imagine a catastrophic event, a collision with another large body in its system, or a gravitational encounter that flings it into its parent star. The dwarf planet is shattered. The event is so violent that the body is completely disrupted, its core, mantle, and crust thrown into space as a new field of debris. Most of this debris would remain in that system, but some fragments, given the right trajectory and velocity, could be ejected into interstellar space. If 3. I-Atlas is one of these fragments. Its strange properties begin to make sense. If it were a piece of the icy crust or upper mantle of a differentiated world, it would naturally be rich in volatile ices like carbon dioxide and poor in the heavier elements like iron that had already sunk to the core. The nickel without iron anomaly could be a specific chemical signature of that parent body's mantle. Its density, potentially higher than a typical rubble pile comet due to being carved from a compacted planetary layer, would help it withstand its rapid rotation. This shattered world hypothesis also addresses the profound size anomaly noted by Avi Loeb and his colleagues. The fact that we have found an object with a mass of at least 33 billion tons, after finding only 2 much smaller interstellar visitors, defies statistical expectations based on models of planetary system formation. We should have found tens of thousands of Oumuamua-sized objects first, but if interstellar objects are not all primordial comets, but also include debris from planetary disruptions, the statistics change. Catastrophic collisions are rare, but when they happen, they can produce a small number of very large fragments. We may not be seeing an inverted size distribution of comets. We may be seeing 2 different populations of objects entirely. One population of small, common, primordial comets, like Borisov, and another population of large, rare fragmental objects like 3 I-Atlas, which are the debris of distant planetary scale violence. We are, in essence, practicing a kind of interstellar archaeology. This object is a shard from an unknown place. Its spin tells us about its structural integrity. Its trajectory tells us about its violent ejection, and its chemistry tells us about the world it once was. The carbon dioxide sublimating from its surface today may have once been frost on a mountain, or ice in a frozen sea on a world orbiting a star hundreds of light years away and billions of years ago. The final, most speculative ideas push the boundaries of known physics. Some have suggested that the object's immense mass and density, coupled with its stability, point to it being something other than a rubble pile entirely. Could it be a single, solid piece? A megaboulder of fused ice and rock, far stronger than any comet we have ever studied? This would require a formation process we do not yet understand, something that could produce a 5-kilometer-wide solid body with the strength of rock but the composition of a comet, and inevitably, given its interstellar origin and anomalous properties, some have invoked the possibility of artificiality. Just as with Oumuamua, the collection of strange characteristics, the unlikely size, the peculiar rotation, the unusual chemistry, leads a few to ask if it could be a technological artifact, an ancient probe or craft, tumbling through the galaxy. But the evidence points overwhelmingly to a natural explanation. The outgassing, the coma, the spectroscopic signature of known ices, all of these are the hallmarks of a comet, albeit a very strange one. There is no evidence that requires an artificial explanation. The universe is vast and creative enough to produce objects that challenge our understanding without resorting to intelligent design. 3. I-Atlas will reach perihelion, its closest approach to the Sun, in early 2026. As it gets warmer, its activity will increase, the outgassing rate will climb, the forces acting on the nucleus will intensify. Will the 16.8-hour period hold? If the self-regulation model is correct, it should. The comet will simply shed mass at a higher rate to maintain its equilibrium. If the contact binary model is correct, it should also remain stable. But if both are wrong, and the comet is simply a very strong but otherwise normal body, the increasing torques might finally overwhelm it. We could witness the rotation rate begin to change, or even see the nucleus fracture and split apart under the strain. Every telescope that can be trained on it will be, from Earth and from space. The James Webb Space Telescope will continue its infrared analysis. Hubble will try to resolve more detail. Ground-based surveys will take photometric readings every single night, tracking its brightness and its spin with ever-increasing precision. We are watching a live experiment in cometary physics. This visitor from another star has presented us with a paradox wrapped in a mystery. It is a comet that spins too fast to exist, yet it does. It releases enormous amounts of gas without changing its trajectory, defying the laws of motion as we know them for such bodies. It has a chemical makeup unlike our native comets, hinting at a foreign and ancient origin. The theories, a self-governing engine of its own destruction, a tightly bound binary pair, or a fragment of a long-dead world, are all attempts to make sense of an object that obeys the laws of physics, but in a combination we have never before witnessed. 3. I-Atlas is more than just the third interstellar object. It is the first one that has forced us to reconsider the fundamental nature of what a comet can be, and the violent, diverse galaxy from which such messengers emerge. The story it is telling is just beginning to be translated.